Hello, this is Mr. O'Brien, and this is going to be part two of the quantum theory of the atom, and this is strictly for honor students. In this notes series, we're going to talk about an attempt to explain why we use Bohr models and how Bohr models help us to rationalize the color of light that we see. So let's get started. You have some experience in the class already taking a look at colors from a spectral tube and then colors from a flame test, experiments that we did. We attempted to energize the matter that didn't have any color, and when we energized it, produced some sort of color that we were able to detect. Like in the neon gas, you saw red, or in helium, you saw pink. In some flame tests of copper, you saw greenish blue, or calcium, you saw red. And then you don't even need to know, you come to the class and know that some colors exist, like the color of a light bulb. When you turn it on, the light bulb has like a little filament here, and the electricity going through this piece of metal makes that piece of metal glow really bright to create visible light. So what's the point of the understanding the Bohr models? So again, we want to understand this visual light, and that how when we energize matter, no matter how we energize matter, how do we see that visible light? Just like the colors that we see when we see, like, say, your shirt or whatever. So what's visible light? So the electromagnetic spectrum is comprised of a lot of different waves, right? From all the way from like the radio waves that we can hear from our AM or FM stations, to our TVs, to the infrared, the little remotes on our TVs, to the little small sliver of visible light that we detect, right? To ultraviolet light, the energy that comes from the sun that we need to protect. We're using sunblock. X-rays, if you've ever been to the doctor's office. And then there's gamma rays, right? So what we're going to be focused on is just this small sliver of spectrum, of electromagnetic spectrum, we call the visible light. Now, light, the visible light, is a very small range of wavelengths of the electromagnetic spectrum. And that light is energy and travels in both waves and particles. Now, I kind of give you a picture here of what waves are, and we'll talk about that shortly, but I just want you to take a look of how small this range that our eyes can detect, that we can physically see, is when compared to the entire electromagnetic range. And for all intensive purposes, for this class, we just want to understand more about the visible light, right? So if you've ever had a chance to check out a rainbow, here's an example of a rainbow from a sky after it rains. And you've noticed that the rainbows has these beautiful colors, very similar to the colors here. Think about this question, man. Have you ever noticed the order of the colors different on different places of rainbows? Possibly not. And that's because the reason is of this, right, which we'll talk about in a second. So two terms that you need to understand more as we go to learn how to calculate this is wavelength and a frequency. So a wavelength is the distance from crest to crest, right? And that distance is measured in small units that we call nanometers, really small. They're so small that 1 billion nanometers will equal 1 meter stick. Okay, so that's how small they are. And frequency essentially is kind of like how many waves pass in a given point. How often, how frequent are those waves? And when the frequency in hertz is measured per second. So how many waves can pass per second, right? So when we talk about waves, right, waves carry energy through space. Like, you know, our energy we get from the sun, right? And that sun is going to, you know, give us Earth energy. The planet is getting warmer. We're getting a nice summer days. We get some energy when it's cold in the class or wherever. We'll go outside and get some sun. Now, that energy travels in the form of wave, and it travels through empty space. And that wave and those energies have three characteristics. They have a length, they have a frequency, and they all move at the speed of light, which the speed of light essentially is about 3.0 times 10 to the 8th meters per second, which essentially is in miles per second, right? It's the speed of light of 186,000 miles per second. So, I mean, that's pretty fast. But considering how fast it is, we are so far from the sun, it takes like a little photon of of light to reach Earth. 8 minutes and 20 seconds, right? It's a long time. Anyhow, moving on. So this idea of that this color red, right, seems to have a longer wavelength than this color blue or purple. The wavelength here is much smaller. Because the wavelength is bigger in red, the frequency is lower. Well, that means that given the starting time right here, let's just imagine there's a starting time. We're taking time to see how many waves pass. The speed of them is all the same. What's different here is that we're going to have less waves per second, right, in the red than we're going to have in the blue or purple. As you can see here, there's more waves. So here's one wave, here's two waves, three waves, four waves, five waves. Versus here, you got one wave, two waves, three waves. So you have more waves per second than you have in the red. Now, what else does that mean? Well, since waves carry energy, how much energy can waves carry? Well, that really depends on this frequency, right? How often do the waves travel? So the more frequent the waves are, the more energy they carry, right? So then, hence, the less frequent they are, the less waves that are going to pass per second, the less energy that there is. So what are some of the other characteristics of visible light? Again, they all travel at the speed of light, right? And the range that we can see is only limited to 400 nanometers to 700 nanometers. And each of those colors of waves have a different wavelength and a different frequency. You can kind of see here on the bottom where I noted Roy G. Biv, this analogy. And you might have heard it. And if you haven't heard it, I kind of matched it up with the colors. R is red for 700 nanometers. And the V represents the violet at 400 nanometers. The O is the orange, the Y is the yellow, the G is a green, and the B is a blue, and the I is the indigo. So it's Roy G. Biv, a nice kind of acronym to remember about the colors of the visible light. So these characteristics of waves can also be quantified. We can measure, we can use numbers to express them, to describe them. And when we quantify them, we use these two equations. And one of the equations, this one identifies the energy trapped in the waves. And the other one describes the relationship between the speed of light, right, versus the wavelength and the frequency. Remember, this is the variable for wavelength, right, and this is for frequency. Okay? And these are numbers, these are constants that are used to describe the speed of light, and this is the constant, the Planck's constant, to help you calculate the energy. Now, you'll never have to memorize these equations, and you'll never have to memorize these constants. You just need to know how to apply them, which we'll talk about later on in this lecture series. Okay. So I want you to pause I'm going to pause for a moment, and hit pause. I want you to think about this question. Given the information about the visible light that you see here, right? What could you say about the characteristics of green light in the rainbow, right? So let me move on to the next question here. So when hydrogen gas is energized, it produces visible light. Two detected wavelengths of hydrogen are shown below. So here's one range or one wavelength of light that we see from hydrogen. Here's another one. Now, you've seen this in class as the color hydrogen. So what I want to do here is I wanted to show you how we can convert the wavelengths. Remember, we learned about nanometers and we talked about meters, right? Two important units of measurements. So I'm going back to when we learned about the moles, how to convert. So the first thing that we need to do is we're going to write our given down, and then we're going to identify conversion factors, and then we're going to apply the conversion factors, and then we're going to solve them. Okay. So again, these are real examples from what you saw in class. We're just going to focus on these two waves that hydrogen produces. So in the first one, you want us to write the given down. So we got the given down, but then you need to identify your conversion factor. So the conversion factor here is going to be 1 meter is equal to 10 to the 9 nanometers, right? 1 billion nanometers. So how are we going to put this? We're going to put this 1 meter on top or 1 meter in the bottom. Remember that we want to cancel our given units, right? So that we are allowed our new unit that we want. And we want to convert this into meters. So our meters is going to be placed above, and our nanometers will be placed below. So this looks like that, right? And so when we multiply 410 times 1, we'll get 410. And then when we divide it by 10 to the 9, we actually have a negative number because we're subtracting, right? And when we go one more step further to clean that up and for scientific notation, we'll move the decimal 2 spots. 1, 2, 1, 2. And as we move it left 2 spots, we'll have to add 2 places. So this becomes minus 9 plus 2 is minus 7. Now, this is 4.1 times 10 to the minus 7 meters. Really, really small on the meter stick. But it makes sense, right? Because nanometers are really tiny to begin with. And this wave is the color purple. Now, how do you know it's color purple? Well, remember Roy G. Biv, right? Red is 700 nanometers, and V is the extreme at 400. If this is like 410, you know this is going to be near violet, so hence purple, right? The other example is this 6.56 times 10 to the minus 7 meters. We'll change to nanometers. Same idea, right? We have the same conversion factor, this one here. And when we plug this one in, however, we do the reverse. We'll do nanometers above and the meters below so we can cancel out the meters. And so as we do this, we get 6.56 by itself. But then remember, we can add these two together, right? It's minus 7 plus 9. And as we do that, that'll give us 6.56 to 10 to the second. And we really don't need to have this scientific notation anymore because this isn't that large, right? If we move this 2 spots to the right, we get rid of that. It becomes 656 nanometers. And remember again, 700 is red, 400 is violet. So at 656, you're looking at somewhere, red to like reddish orange or something like that. So I place this down as red, right? Again, Roy G. Biv. Okay, 700, 400, right? So here's an example. I want you to practice this one. So here's another wave produced by hydrogen, and that's detected to have this wavelength size. Oopsie, minus 7. That's how it should be. I want you to convert to nanometers and tell me what color wave you have. If you have any questions on this, hit me up at tutorial. All right. Now I want to talk to you about how to calculate the frequency. So again, same thing. When hydrogen's gas is energized, it produces a purple visible light. And so we talked about that one of the wavelengths is 410 nanometers. Let's talk about and calculate how often that wave happens per second, hence the frequency. Well, the first thing that we need to do is we need to know which one of these equations we're going to use, right? We're going to apply them. So we're going to apply this one because it contains wavelength and frequency. So we have to rearrange the equation, right, to get our frequency by itself. Next, we're going to make sure that we use the correct units. We can't just use 410 nanometers because our unit of our speed of light is in meters. So we can't use this. So we have to convert this guy into meters, just like in the last slide that we did. So once we do that, then we just solve, right? You get 3 divided by 4.1, you'll get 0.73. You get 8 minus my negative 7, and you'll get 15. And we move this to scientific notation, fix it, move it to the right, becomes 7.3 to the 14 because we subtract it, right? Remember that? So what does this mean, man? 730 trillion waves per second, 100,000 million billion trillion. That's how many waves per second our eyes can detect when we see the color purple, right? All right, so you try this one out. The wave that we also described in the previous slide tells us that there's a wave of hydrogen at 6.56 times 10 to the minus 7 meters. Now, I want you to calculate the frequency of this wave and then compare the energy in this wave versus one that contains 410 nanometers. Talk about the energy, all right? The next one here, the wavelength. So in this case, we've talked about already 2 colors of hydrogen that produces 410 nanometers and 656 nanometers. Yet hydrogen produces a total of 4 distinct spectral lines. Those lines you saw through the spectral tubes. One line is detected to have a frequency of 6.17 times 10 to the 14 hertz. I want you to tell me what the wavelength in nanometers is of that frequency. So again, you're going to need to try to figure out which of those equations on the right-hand side we need to know, or we need to use. And it seems like we're going to use this equation again because this one gives us wavelength and frequency. If we rearrange this to find wavelength, we'll get speed of light over frequency. So then when we do this, we'll get these two numbers. We'll divide these out. And that gives us this number. And then we'll get the 8 minus the 14, which will give us minus 6. And then as we move the decimal to the right one spot, we have 4.86. And then remember, we have to minus it because we moved to the right to the negative 7. Now, here essentially is our wavelength, but we want to convert this into nanometers. That was like 2 slides ago. So let me show you again how to convert to nanometers. Right? We have our given units. We have our conversion factor, which is the same. And so 4.86 times 1, which is 4.86, and minus 7 plus 9, which gives you so it's power of 2. And so again, this isn't really big enough to keep in scientific notation, so we'll change this to a regular number, which gives us 4.86 nanometers. Okay, and this color is going to be like I don't know, maybe like somewhere near a teal color or something like that. Remember Roy G. Biv? So try this out. Try to find frequency of this wave. So another wave produced by hydrogen is detected at 6.91 times 10 to the 14 hertz. I want you to calculate the wave and tell me what color wave would it be. Now remember, to answer that question, you need to remember Roy G. Biv, right? So try that out, and if you have any questions, hit me up at tutorial. So our last slide here, right? So how are Bohr models and then the visible light related? So I want you to go back and think about the hydrogen tube that we saw in class, the same one we've been talking about in the lecture notes right now. So how does that produce that kind of like purple bluish color, right? So the only way to see it is when we turn on the electricity. When energy comes into that tube and goes out of that tube, the gases in here are producing some sort of color. Well, the atoms inside those gases, electrons are absorbing energy from those from the electricity. So the electrons of the atoms of hydrogen are essentially jumping up to new and higher energy levels. This is called being excited. Now, they don't last there that long. And so what ends up happening is that they eventually crash back down to what we call their ground state. The ground state is where they started at. When they do that, they release color. You see, this is why, in order to see color, you need to have some sort of energy. In a pitch black room, you won't be able to see color. You can't detect color unless there's light. So hence you turn on the light. And so light will give you energy, enough energy that you can see maybe some color of like a t-shirt or something. But the energy is different depending on the type of matter that you want to energize. When they release that color, you're going to see a unique set of waves. And those waves are because as those electrons jump up to new energy levels that don't exist, they're excited states, they need to crash down. As they crash down from level 1, say, all the way up to level 3, and they jump back down, they're going to be releasing some energy. And depending on how much magnitude of electron transition they do, will tell you the amount of color or tell you type of color. And some of them are so great that they don't even show a color because we can't detect it. Because remember, our range is 700 to 400, right? So if you notice here that the ground state is always at 1, but we can't detect any color that goes from the electrons of 1 to, say, 3 to 1 or 2 to 1, because those are too much energy. We can detect much lower energies, right? And even between these guys here, you'll notice that the red color is between 3 and 2, right? But the kind of like teal color is between 4 and 2. Well, why? Because there's more energy in this jump from here to there than there is from here to there. And so the more energy, hence you get the more color, because when you have a violet, like, let me make this violet. When you have violet light, like back in our notes, we know that we have really, really tiny wavelengths. And so we're going to get more waves per second, more frequency, right? Which hence will equal to more energy. Versus, say, in red light, since the waves are longer, right? Longer waves, okay, we're going to have less frequency. And when we have less frequency, we're going to have less energy because the amount of waves are less. So essentially, when we energize matter, it gives us the spectral lines that we see. This kind of coding, this barcode that you see, you saw in the lab and the experiments in class, this essentially is a result of exciting the electrons to new areas beyond where they're not normally, and observing how they transition down gives us that color. That's how we get these spectral lines. So let's try to quantify energy of hydrogen. So I want you to calculate the energy of the red light. So let's find out how much energy that this red light wave produces. So you might be wondering, well, wait, let's just use this one because it has energy in it. But we can't yet because the only thing that we're given is the wavelength. So we need to first find what the frequency is. So when we find the frequency first, right, then we can eventually use the frequency to find the energy. So we'll find the frequency, right? We know what wavelength is, but remember, we can't use this wavelength because our speed of light is in meters. So we need to convert that. If you don't remember the conversion, go back to the video and look at our conversions. So that's our frequency. When we get these numbers again, we divide these two numbers out. We'll get this number. We'll get these numbers here. We'll subtract those ones. We'll get that one. And so here's our frequency of that red light, right? About 457 trillion waves per second. Now that we know the frequency, we can plug it into the energy equation, and using Planck's constant, a number that you'll never have to memorize, we can plug these two together and find the energy. Multiply that number times that number will get you 30, right? And then these numbers are added, right? Will get you 20. And then we need to change this back down to a scientific notation, move it to the left. We'll add 1, right? And this becomes 3.03 times 10 to the negative 19 joules. Now you might be wondering, wow, that's really small, right? Why is it so small? Well, consider this. This is just the energy in one valence electron transition, just one. But if you're seeing color, right, you're experimenting with more than one atom. Remember, this is the idea about the macro scale. So we're experimenting with a mole of atoms. So in reality, the amount of energy that you're looking at when red light comes at you is way more energetic than this. These calculations just talk about the electron transition here. One electron transition right there. Okay? All right. So I want you to practice that idea, right, for calculating energy with this problem here now. Same idea. You're going to calculate the amount of energy in 486 nanometers. So if you have a hard time, give me a heads up on a tutorial and we'll talk about it together. All right? Thanks.